So let me let me introduce our speaker, Professor Anar Dosi. Yes, no, and he will please everybody listens. Please, Anar, begin.
Okay, yeah, thanks. So let me share my screen first, if it's all right. Yeah, please let me know. Is it all fine?
Yeah.
With my...
Yes. We
Okay,
see
yes, thanks.
spectral models over an affine scheme. Slide presentation. Excellent.
Okay,
Yes.
Okay, yeah, many thanks for the invitation. I'm happy again to have a talk in our traditional seminar.
Yeah.
Hopefully I will continue the same
Yes.
spirit.
Well,
okay.
it depends on many factors. Okay.
yes. Okay. Let me switch this one there. Okay, so first of all, it's all about algebra, actually, commutative algebra, but from point of view analysis. There is some functional analysis vision for that, or operator theory vision. So we're going to find some links between spectra. There are various spectra in algebra, and so my task to understand whether they are sort of operator spectra. Yeah, so all these works, they published in my free papers here. So now I'm working on the last one, so trying to modify is actually poorly written here. So, and let me say that it takes too much energy to understand the algebra and then all this digestion process. For example, the first one, it took all my summer playing the mathematical ping pong was the referee. Eventually, so I accepted and published. So, what exactly? So we want to understand the spectra, how it can be converted to spectra of operated tuples. Especially my first task to understand associated primes, why they are actually eigenvalues. Yeah. And next, we're going to try to explain the gap between support and Taylor spectrum, which can be described in terms of scalar tuples, actually, over the ground field. Well, in a non-commutative case, we used to think that the spectrum, actually, they are sort of reducible representations of the basic algebra. Well, something like that will happen here, but in terms of field extensions. Well, I will explain. Since it's a commutative case, so it will be sort of generalized characters. Okay, so let me turn. Yeah, let me start with elementary stuff. I will explain everything here. So, for example, what is an associative prime? So we're going to fix a commutative ring, unital commutative ring R. So that's my affine scheme, set of all primes, and M, B, and R module. So first of all, an ideal prime. What does it mean prime? Prime, we mean an ideal whose complement is multiplicative set. That's called a prime. So prime is said to be associated to M, or by somehow related to M, if it can be written like annihilator of some element M, little m of the module M. Since P is proper, so this M is automatically non-zero. So look, that means annihilator, or zero divisors. So the set of all primes associated to M is called, from our terminology, well, I call it like point spectrum of the module of a scheme. But why point spectrum, you will see later. Now let's accept like sort of spectrum. Okay, this object is well-known object of the commutative algebra. So you can see the independent chapters in commutative algebra books about associated primes. Yes, next, we're going to take the support. Support of the module means set of all primes whose localization at P is non-zero. So set of all those primes, and P is not zero. So you're localizing with respect to a complement of P, making them invertible actions over M. So that's called support. You're going to take the closure in this scheme, in this topological space X. That's called spectrum. Again, this is our notation, spectrum M over scheme M. That's sort of elementary stuff from commutative algebra. Next. So what is an associated prime? If you get associated prime, so you can take its quotient, and since it's an annihilator, you can kill the annihilator, and eventually all the stuff will be embedded into M. That's R modular injection, Rp into M. So that's sort of criteria. So P is associative means this quotient embedded in M. For example, if you take this module, R over P, the point spectrum, since it's a domain, no zero divisors here, so the point spectrum will be just single P and nothing else. Yeah, look at this sort of operator behavior, probably you know. So if you have an invariant subspace, or if you, well, no subspace, submodule here. If you have an invariant submodule N, then point spectrum of N is inside of M, and this point spectrum can be decomposed into N and the quotient, M by N. That's sort of familiar property of spectrum in operator theorem. Next, if your model decomposed into two submodules, spectrum also would be decomposed like that. Well, for example, if you take this Z, and let's take this module, Z over 2 plus Z. Right, so then you can easily calculate the spectrum. Point spectrum is going to be this one, union this one. So this has only one prime, which is 2, and the other one is 0. Look, this is my computational spectrum for M over X. Okay, another example, we can get this polynomial algebra of a field. Get this maximal ideal, X, Y, and K. This K means trivial module, or what is maximal ideal. Again, we have a decomposition. We can calculate the point spectrum as a union of two pieces, right? Two parts. This one is, again, no zero divisor. We have just only 0. And the other one is just single maximal ideal, X, Y. But between them, we have another primes, for example, X, which is out of the point spectrum. So the point spectrum could take some gaps. You may have something else between them. That's quite normal, right? There's a certain primes. Okay. Well, but how we can detect these associated primes? How we can find them out? Just look, this one is associated. So look, I mean, the standard moment. So what do you do? Get this annihilators of modules. I mean, of module elements, non-zero. This is a family of ideals inside of R, right? And suppose we have some maximal element of this set C. For example, annihilator of X. So my claim is that then that P will be exactly associated prime that we are looking for. Come on, let's prove it. So what we have to prove that if A, B is inside of P, but B is out of P, then we have to prove that A is inside of P. That exactly means P is a prime. Yes, look, AB is in P means ABX is 0, right? Because it's an annihilator of X. B is out of P means BX is a non-zero element of the module M. So that means A belongs to annihilator of B of X, right? But P is annihilator of X. Annihilator of B of X will be bigger than this because ring is commutative. Whatever annihilating X is going to annihilate BX. So, but this guy from sigma as well, is it? And P was maximal, so P equals annihilator B of X, right? But A belongs to annihilator B of X, so A belongs to P. That's it. So P is a prime. Look, that's a one way how you can detect associated primes to module M. So that's a moment why we need this assumption to be Noetherian ring. Let me recall the ring is Noetherian if any set of ideal it has a maximal element. So that's exactly the case. If R is Noetherian, then this set has a maximal element. So we have enough associated primes. So look, that's the sort of criteria. M is not zero if and only if its point spectrum is not empty. In the case of Noetherian. So if you unify all these primes, you're going to get zero divisors of the module M instead of all ring elements that's, annihilating some elements of the module M, right? Okay, so we understood. So point spectrum, how does it respond to M? So if M is non-zero, if and only if point spectrum is non-empty. Okay, now let's take Noetherian ring, M is a module. Now take any prime Q from X. So let's pass to localizations, RQ. RQ is also Noetherian, so we have this criteria again. MQ is non-zero, if and only if associated prime is non-empty to point spectral. But since R is Noetherian, we know what they are, right? The set of all primes which is inside of Q. That's standard manipulation from the commutative algebra. So this one provides us some link to support. So MQ is non-zero if and only if Q belongs to VP. That's the means set of all primes which contains P. For some P from my point spectrum. In particular, you can apply Q equals P, so all associated primes is actually their support primes. So sigma P belongs to my support. And support is just can be expanded like a union of all the sets VP. So every support prime contains some P prime. Or you can say that every spectral value contains some point spectrum, an element from the point spectrum. In particular, minimal primes from here, they will be among this point spectrum, minimal primes. Okay. Oh, look at this first triangulation result. It's an abstract form, but I will explain why it's all about upper triangular matrices. Still no matrices here. It's just some general result from commutative algebra. Say R is Noetherian ring, M is Noetherian module. Then point spectrum is finite. And there is a chain of submodules whose gaps looks like that R over PI some primes, so that associated primes, they are inside of this set. It's not a set, it's a multiset. And this multiset is inside of support. So what is a multiset? The problem is that whenever we're getting these gaps, a certain prime could repeat several times, so-called multiplicity. So that's why you should include P with the multiplicity several times. That's why it's a multiset sort of terminology, multiset. Yeah, this is some interesting result from commutative algebra. Well, later on we're gonna convert it into some operator language. It will be interesting. Okay. Well, for example, let's do elementary example. Let's take R as Z, modulus Z over 12. So let's calculate support. Support as Z over 12 means set of all prime ideals containing 12. But we know they are divisors of 12, right? Prime divisors, prime factors. We have 2 and 3. So this is my support. Annihilator, well, you know that the annihilator of 6 will be 2, right?
Anar, I'm sorry to interrupt. So what is V? Is it a set of prime containing the given ideal, or
Oh,
what?
yes, that's right. So let me show you again. So where was my V? So I started to talk about V should be. Oh, just a minute. I thought that I said about the V. Look, it was here. Yes, that's right. So V is a set of all primes containing this ideal P, whatever you have here. Well, it's a standard notation from German. I mean, from the commutative algebra. Yeah, that's right. Thanks. Okay. Probably faster here. Yeah, that's V. Set of all primes containing 12. So we have 2 and 3. Annihilate of 6 is 2. Annihilate of 4 is 3. So can you see both are associated primes? So both are from point spectrum. 2, 3, they are the same. So this is my point spectrum. Now let's find the same chains. I mean the possible chains for M, as we said about triangulation result. So what has been chain between chain inside of M means actually a chain of ideals containing 12 and Z, right? That's a between that. So look, possible chains between 12, 6, 3, Z. If you look at this gaps, 6 over 12, 3 over 2, Z over 3, you will get 2, 2, 3. Can you see 2 multiplicity has 2, so repeating twice. Well, next possible gap, 12, 6, 2, Z. If you look at the gaps again, 6 over 12, 2 over 6, Z over 2, you're going to have 2, 3, 2. Another chain, 12, 4, 2. Well, again, if you could look at these gaps, you can have 3, 2, 2. Look, it's not a big deal. So finding this sort of chains and calculating the gaps, right? Okay, so now let's switch to our stuff. So let's start first. Fix the field, K. It should be algebraically closed field, K. Let's finally generate algebra over K. We used to say algebra find extension of the field K. Look, X is a tuple of elements, X1, Xn, so it's a commutative algebra over K. X is a spec of R, set of all primes. M, R module. Well, we know R is a quotient of the polynomial algebra, right? K of X. This is a polynomial algebra. X, again, the same multiple, X1, Xn. So look, that's my quotient for some ideal A. Well, again, it's not so hard to see that. So X is actually a set of all primes containing A can be embedded into spec of P, right? But spec of P is our affine space. That's a scheme. Look at my notation, index K, we fixed here. So that's scheme. So X is a closed subset of this affine space up to homeomorphism, right? Okay, so we identify X with a closed subset of A and K. Okay, so my task is to show that in this identification, actually, spectrum will be invariant. Spectrum will be the same. Again, let's take P from V of A from A and K. P contains my ideal. So that means P should be identified with P prime. P prime will be from my X, right? P of A. So if you calculate localization R with respect to P prime, right? Because P prime is an ideal of R, so this is a ring localization. Since complement is the same as a P minus P, I mean P minus little p, so we have a module localization, they are the same. But the module localization means P with respect to P tensoring R over P. So you can adapt the same for the module MP prime, RP prime over M. RP prime is P over PR. So you're swallowing the R, result P over PM. That's exactly localization as a P module, MP. So that means the supports of the module as a R or P, they are the same. Right? Support the same. Well, what about associated primes? So I told you, what is an associated prime? So this quotient should be embedded inside of M. But look at the quotient. If you take the quotient with respect to P prime and P with respect to P, they are the same. So since all the rest they are compatible structures, so this guy embedded into M, if and only if P over P is embedded into M. So associated primes, they are the same as an R module or P module. Okay, so now let's summarize what we got. Point spectrum X over scheme X is the same as a point spectrum M over affine space. They are the same. Next, spectrum, as we called it spectrum, support M closure. Yeah, by the way, in the future, you will see that, this one is actually a Putinar spectrum from analysis, analog of the Putinar spectrum, Mihai Putinar. So again, they are the same, like supports are the same. So this one is going to be spectrum of M over affine space. So the spectrum, they are the same, right? Okay, so we can easily look at the case of M over P. So polynomial action will be enough for us. Okay, look, that's a link to eigenvalues. Where is my eigenvalues? Let me say. So suppose P is an associated prime. As you know, what is that, right? Annihilator of some element, M. Okay, suppose my P is actually a closed point. Look at my notation AN without K. That means set of all closed points, or that means set of all maximal ideals of the polynomial algebra P. But since we have assumed that K is algebraically closed, that means P is actually X, this tuple minus some point. A is a scalar tuple from AN. So that means point, right? X minus A, this is my maximal ideal. So this is my A. Okay, so this guy, X minus A, annihilating M. So let's plug in here, X minus A times M is 0. But we know the action of X over M is given by means of little x's, right? So XIM equals AIM, I between 1 and M. Well, look, that's exactly means this tuple, A, is actually a joined eigenvalue, right? And M is a related joint eigenvector. That's it. So if you get our point spectrum, restrict to closed points or maximal ideals, we have the known from operator theory point spectrum. Look, that means point spectrum, set of all A's from, if you wish, K power N. There is non-zero M, XAM equals AMA. So this set of all eigenvalues, actually. Yeah, that explains the link between point spectra from scheme theoretic sense and this operator sense. And we can easily describe this link. So this gap between this scheme version and operator version, right? So we know this gap now. Okay, so first task done. We know this gap. Second task, how to understand this one. So we know this closure of support or sometimes just support intersection with AN. What are maximal ideals here or closed points? Okay, to do it, but first let's again talk about a bit in general spectral theory. I mean, let's relax a bit. Started with elementary stuff. What is a spectrum? Okay, we have again algebraic closed field. Rk is a commutative of K algebra. M is our module. So M is a vector space, right? K. If you fix element of ring, so this T defines a linear transformation, right, over M. So we know what is a spectrum. Set of those A such that T minus A is not invertible over M. So this sort of some points from the affine line or from cages. Or you can introduce like that. Look, this is my M. This is a simple complex. So this complex should not be exact, right? For those A. So we have homology groups, H0, H1. Okay, but this generality is actually not good. So look what may happen. Spectrum can be empty. So for example, take R as Kx, M, fractional field, T is X, is a multiplication operator. Then for every A, T minus A will be invertible. Look, 1 over X minus A. So spectrum is empty, nothing there.
Yeah.
Next, spectrum could cover up all space. I mean, all line A1. For example, M equals R is a polynomial algebra. T equals X is a multiplication operator. Spectrum will be all real line. I mean, all line K. Well, next, let's take this coordinate ring of the hyperbola, quotient with respect to this ideal, xy minus 1. Again, T equals X. Little x means the same representative of X in the quotient. So if you calculate the spectrum, you will see A1 minus 0. It's an open dense subset. Yeah, it's all about Zariski topology, so topology is weak here. Okay, look what's happening with the spectrum in general. So we can tolerate by somehow the last two cases, but that's not good. The first one, right? Spectrum is empty. This is not good. First, we need to solve this problem. Okay, look, let's turn back to again the same result I told you about triangulation, modifying a bit in the following sense. Look, RK is again algebra find extension, M Noetherian R module. T from R, then spectrum is never empty. That's good. How to calculate the spectrum, like in linear algebra? We can take this chain, whose gaps are R over Pi. Do you remember this one? Associated prime among P1, Pn. That's inside of support. So spectrum can be calculated over gaps. Look, T has an action over this module, R over Pi, getting the spectrum and getting this union. So that will be your spectrum. So you can do some derivation from here. Spectrum is either finite set or it's a dense subset of A1. The two possibilities for spectrum, either finite or dense subset of A1. Look, that's a one way. It's much better than nothing, right? Spectrum is not empty, so you can calculate using the gaps there. Okay. Well, that's possible. You have big gap, for example. We know it. X over polynomial is going to be A1. You can do this one. Mm-hmm. But something interesting happening whenever a module has a finite length. I will explain what has been finite length a bit later. So those who know, that means just we have a Jordan-Hölder series whose gaps are irreducible, right? But I will explain below. Then associated primes, they are maximal. M is a finite dimensional vector space. In this case, X is a triangulizable. Now look, this is a lower triangular matrix. This is my spectrum. A1, AN is here. This is diagonal elements which consist of fine spectrum of T. How you can get this A1, AN. Again, I will explain below it. Okay, continue our spectrum. Concept of a spectrum, we can easily generalize. This is well-known construction of Kosul complex. Get X, get A, X minus A is another tuple. We know what has been Kosul complex, right? That is differential, how this operator is acting over M. And for homology groups, we used to write A, G, X minus M, M. They also are modules of the homology groups. Okay. We can also define the index. This another algebraic Fredholm theory. So if dimensions they are finite of the homology group, we can define the index here. Well, we know what is an index, right? So from linear algebra, it's a difference of the dimension of kernel and co-kernel, whenever both are finite. In the finite dimensional space, we know the index is 0. So now let's summarize what we got. We can define the Taylor spectrum, set of all A's, like in operator theory, Kosul complex is not exact. Then my point spectrum of the tuples actually means set of those A's such that nth homology group is not 0, right? That's standard. Okay, now let's formulate the first result. First part we proved already. Anyway, let me formulate all together. Let R be a finitely generated algebra extension of the field K, algebraically closed field. X is a affine scheme, M an R module. Then point spectrum intersection with AN, close point, will be exactly my point spectrum. We proved it again. If M is Noetherian module, this is non-trivial fact, then spectrum, that means support, intersection to AN, that means closed ideal, closed points or maximal ideals from support will be exactly representing Taylor spectrum of X over N. So Taylor spectrum turns out to be non-empty closed subset whose closure in the affine scheme will be exactly my support. Look, there's a nice link between sort of Putinar spectrum and Taylor spectrum, right? So in a very algebraic case, so the points from the P, if they are maximal ideals, that's exactly representing Taylor spectrum. So primes from support are we can call that as primes from support. They are scheme theoretical spectral values, if you wish like that. Look, this is our first result explaining the link between operator spectra and algebraic spectra. Okay, I told you about the finite lengths. It's interesting always find dimensional case. Let me say a few words about it. So what does mean R module has a finite length? Finite length means there is a composition series. Sometimes it's called Jordan-Hölder series of submodules whose gaps are simple modules, right? We know what is a simple module. If there is no non-trivial submodule of it. They look like that out of a maximal ideal, right? Out of M. Okay, so that means finite lengths. But we know that the localization is quite a powerful functor. It's an exact functor. So you can apply it directly to all the gaps, to this chain. And look, this quotient, it's if you localize by means of with respect to some prime P, is going to vanish if and only if P is not M. Since all my gaps, they are very restrictive, so it can only admit localization whenever P is M, non-trivial localization. Okay, so if you apply your localization to this chain, you will see that only these ideals, M's, will survive, right? Only these M's from these gaps will survive. M is an annihilator of this quotient. So support promptly turns out to be maximal, the set of maximal ideals of M. So every prime from support is maximal. But I told you every prime contains associated primes, right? So some associated prime. So associated primes, they're also maximal, right? They also consist of maximals, and they are the same. Look, that's a moment if assume that once module has a finite length, automatically all support maximal and associated primes, they are equal. That's a reason why in fine dimensional we have just equality of all spectra. Now you will see. Okay, conversely, if associated prime is inside of maximal, consists of maximal ideals, M is a Noetherian module, then you can use that triangulation result for M. You will see that that chain is actually a composition series. So that means modulus has a finite length. So for a Noetherian R module, the following statements are equivalent. M has a finite length. Support consists of maximal ideals. Associated primes consist of maximal ideals. All these three statements are equivalent. In this case, look, we have this nice equality. Support, maximal, associated primes, they are the same. Okay, now we need just to convert to operator language. Let's see, what is that? Look, what is that? RK, finally generate algebra extension of the field. M, R module, whose length is finite. X, an operator tuple, so that this gap is integral. Again, those who don't know what is an integral extension, you can just assume that K of X equals R. That's enough. Integral extension plays a key role as an analog of the case whenever a spectrum should be preserved. Spectrum, this gap doesn't affect the spectrum. Anyway, this is a general result. Kx is integral. Then all the spectra are equal. Look, point spectrum operator, point spectrum, scheme sense, spectrum in the scheme sense, and Taylor spectrum, X of M. They're all the same. And Kx module structure is actually triangularizable. And you can also calculate index there, since all homology groups will be they're fine dimensional, so index will be 0 for all points. Index is 0 everywhere, just. Well, proof was almost done, but let's do it. If R is Kx, you can reduce the case R is Kx, applying the previous result. Associated, support, maximal, they are the same. Now you need just to apply the previous result, right? You will get equality of all spectra. So you have a Jordan-Holder series, right? All the gaps will be K by Zariski, Newton, Satz. So that means you can choose a basis. This is your associated prime. Look, all your tuple looks like that. On the diagonal, we have this spectral values. So it's a triangular shape. Look, this analog of the operator operator theory result, right? On triangulation. Well, calculation index is not a big deal since it's all finite dimensional. So you can index can be reduced to Euler characteristics. You're just calculating dimension of the Kosul complex members, right? Terms. And eventually you're getting 0. Just index is 0. Okay. So second task also done. We understood the link to operator theory. The next one, to understand the gap between spectrum, in the sense of Putinar spectrum and Taylor spectrum, right? What stands behind the Taylor spectrum inside of support? So, from complex analytic geometry, we used to say, what's a gap between Putinar and Taylor spectra? It's not so easy task to understand. But in purely algebraic case, it can be done. Okay, so let's review again. So spectrum intersection with closed points, that's Taylor spectrum, right? And I told you non-commutative case is all about irreducible representations of the base algebra. So what are you doing here? Let's see. Okay, we have a field K. Let's define a scalar n tuple over K. That's indeed a tuple, but not from K. That's from some field extension. So there is some field extension, look K of A, depending on A, by the way. It's a special field extension defined by means of A, so that if you take the fractional field of the K subalgebra, it will be K of A. So what is that? This is a tuple here in K of A. You're taking subalgebra, K subalgebra, generated by this tuple, and inverting, looking at the fractional field. So you will end up with K of A, right? So what's the meaning of that? So tuple A defines the representation, right? K representation of the polynomial algebra to K of sending the variables to my A of I. That's sort of polynomial calculus of the polynomial algebra, whose range will be K subalgebra, is it? K of A. So look, that's my assumption. Fractional field of K of A should be capital K A. Okay, this tuple defines a prime. Since no zero divisors inside of K of A, so you can look at the kernel of this representation. Kernel of the representation will be exactly prime ideal. So using this language, actually, you can identify as affine space with the set of all those scalar n tuples. They are the same. There is a bijection between them. For example, the closed points. So what is the closed point? Scalar tuple from K, actually. So that means K of A is just K, right? So A belongs to affine space. A defines the character. That's exactly character, right? Homomorphism from P to K, whose K of K is K. And so one-dimensional, irreducible representations, if you wish. Okay, so having this representation, let me show you again. So look, this representation, you can consider image of any polynomial by means of this representation. F, I mean, for example, look, if you get F, you can calculate its value, F of A. Let's say this is a value F at A, right? Through the polynomial calculus. Using this construction, so you can define open sets, principal open sets. So that's exactly D of A, set of those A's, F of A is not zero. Because F has an action over all representation. In every representation, it has an action, so you can calculate the value there. This is a principal open subset. Well, we can define a partial order between this scalar tuples over K. So we used to say A less than or equal B if there is a connecting map from K of A to KB, so that this diagram commutes, right? In this case, if you restrict this T to the subalgebra, this is going to map subalgebra to subalgebra generated by B. So it's a K homomorphism. So this is a partial order structure, I mean, in AKN. This actually corresponds to inclusion of primes. So on the level linear algebra, you can easily prove that A less than or equal B if and only if kernel of A is inside of kernel of B, right? So it's sort of the analog of the inclusion. Okay, so look, closed set, a reducible closed set of those B, which is B is more than or equal A for a unique A, since it's a reducible closed set. Okay, now let's see how we can define this spectrum. MP module, again given by X, A scalar n tuple in a field extension. So look, we have a field extension. What I'm doing, I'm extending my M. I mean, Ka tensoring over K to M. That's standard field extension process of the vector space M, right? So this this one, Km tensor in K, turns out to be a Ka vector space, right? By means of standard field extension. So you can extend the operators there as well. Look, 1 tensor in X. This again, operator tuple, mutually commuting operators. But now my A from this field, so I can look at this difference. 1 tensor in X minus A. This another N tuple. So look at the moment. Look, my spectrum is actually a set of those scalar tuples such that Koszul complex is not exact. So description is very similar to Taylor's spectrum. You see, set of those A such that Koszul complex 1 minus X, 1 tensor in X minus A is not exact. Well, look, if A belongs to little k, then all this construction actually means Koszul X minus A M, right? We are turning back to original complex. Once A is a character or a tuple from K. So this one exactly explains why we have this equality. If you restrict to closed points, you're getting original Taylor spectrum, right? So look, that's a link between Putinar spectrum and Taylor spectrum. So what's it? Well, finally, we can describe it. So we can describe spectrum completely. Again, there's not a big deal here. It's just every closed sets can be decomposed in Noetherian topological space, can be decomposed into irreducible components. Look, this is my irreducible components here. VA1, VAR. So B from spectrum, B should dominate one of these AJ. So you have a fine number of minimal elements from spectrum, or minimal number of scalar tuples. They've completely defined the rest. So non-exact Koszul complexes, fine number of them, actually define all the spectrum here. Okay, yeah, final task is all a few words about spectral mapping theorem. So in general, we have this spectral mapping theorem. It's a Putinar spectral mapping theorem, and in a very algebraic case, we have schemes, we have an amorphism, M in an R module, then M has an R prime module, and we have this map. But pay attention here, we have a closure here. This is a closure. A closure is not good in this theory because topology is so weak, it can cover up so big space. Okay, so you can apply, for example, to this case, R prime is inside of R, M is R module, then support is dense here, right? Okay, but luckily we have this nice result for Taylor spectrum. So algebra find extension, M Noetherian R module. Then we have this spectral mapping theorem for operator tuples. But pay attention, this one may not be closed. Even in the case if it's closed, the image of P may not be closed. So nonetheless, the formula works. Right? This one explains all these issues happened with this in general spectral theory. But nonetheless, this result is true. So that's not the case like in analysis. In analysis, we had this one is always compact set. P was a continuous map. The image always was closed, right? But that's not the case here. Nonetheless, this very algebraic result shows you what's happening with the image of the spectrum under mapping P. Well, you can apply to a single element. And also we have sort of index stability result. If we have this gap as integral, then Y is another tuple generating the same maximal ideal, then we have equality of both indices there. Okay. Yes, what about for point spectrum? Again, we have the following spectral mapping theorem. It's also quite a general. If R prime R is a ring extension, R is Noetherian, M is our module, then we have this spectral mapping theorem for point spectrum. By the way, point spectrum behaves much better without any closure there. Look, if this gap is integral, then we have also a spectral mapping theorem for supports without closure. But this is not my result. This is a classics again, Krull, Cohen, Seidenberg theory. This independent chapter, for example, in commutative algebra. Look at the Bourbaki independent chapter, all about this extension of primes. This actually was all about spectral mapping theorem, right? In the case of integral. So that means the concept of integral, that means the spectrum should be preserved whenever you're passing from R prime to R. Okay, yeah, some examples. Again, you can see examples. R prime Z, R is Q. So if you look at it, X, support of M is 0. But if you look at the X prime, it's going to be very, very big. I told you in general. But for point spectrum, we have equality. There's another example for K-algebra extension where you can apply the point spectral mapping theorem. So it looks fine. Okay, final example from geometry. Let's switch a bit toward geometry. So Y is an algebraic set, is coordinate ring. Then what's happening? The Y is actually a support intersection. Well, we know what is an algebraic set in AN without K. That's a closed points. That's exactly my Taylor spectrum of the operator tuple over R. X is an coordinate functions acting over R. Point spectrum responds to isolated points of M, of Y. So point spectrum detects just isolated points. Okay, so what's the meaning of that? So interesting side. So every algebraic set, or something you can assume like variety, is actually generate some local homology groups. At every A, for example, you can calculate 0 homology group, which is always non-zero due to Nakayama limit. The last one responds to 0 divisors. The first homology group is also interesting. I did some investigation in this direction. So this responds to singularity of Y at A. And it can be shown that its dimension can be really high, depending on singularity. How deep singularity do we have at A? So what about the rest, HG? We don't know. So probably there are some material in algebraic geometry trying to understand, for example, second homology groups and so on. But anyway, this is nice. It shows you, look, that's a link. It's all about spectrum and Kosul homology groups. And it's also preserves some geometric invariance of the variety of Y at that point A, right? Yeah, that's also interesting. So anyway, I don't know about this direction, so probably they have. Yeah, okay, let me stop here. Yeah, thanks for your attention. Sorry if it was so boring for you.
No, not at all. So thank you very much, Anar, for indeed very interesting talk. I did not know before what is Putinar spectrum. Okay, so what are questions?
Well, I have a question about, well, it's not exactly a question, but just a remark, or maybe a question. Well, if we look at the, let's say, classical situation, I mean, about modules over algebras of holomorphic functions, which were studied by Taylor and then by Putinar, then, if I'm not mistaken, there is a result that for Banach modules, the Taylor spectrum and the Putinar spectrum are the same. Is it correct?
Not. But it depending on top of if Stein spaces, that's not true. But probably if your space is good, I mean, probably there is some terminology in complex geometry. they should be like a polydisc or something very good shape. Like if it has a very good shape, then that's true. If not, never.
But the
So
question
that's
was,
exactly, yes, that's exactly depends on the structure of space. But in
And,
general, it's not true. Yes.
And
So
in
as-
your situation, I mean, in the pure algebraic picture
Yeah.
for modules over commutative rings, are there any good classes of or modules for which the Taylor and the Putinar spectra are the same?
Yes, well, would be nice. Yes, I don't know. Yeah, it's a good question. So probably, yeah, it can be done, but probably again well, okay. So for example, the finite dimensional case that's trivial for you, maybe is not good. Yes, in general, it would be nice to inspect some classes where probably the same, but probably as soon as the scheme will not contain maximal ideal, that won't be true, because Taylor spectrum, as I have shown here, is all about closed ideals, right? Closed points. So as soon as we have something extreme cases, whenever we have extra points out of closed, that won't be true. So that's why I'm not sure in general. Yeah. Anyway, this is interesting. So yeah, thanks. I don't know. Would be good. Yeah. But as you know, this is a very algebraic case, right? So situation is so fragile, so it's impossible hard lever to keep. So, you know, the spectrum is not closed. Image of under polynomial may not be closed. Even it can be dense. So all the bad cases, but nonetheless, this spectral mapping theorem is true. That's good.
Yeah.
All that we can say. Yeah. Okay. Yes.
Okay, other questions? Okay, no, as always, it's very interesting to hear you, Anar. Thank you again. And
Thanks.
let us, all of us are grateful to our speaker. So next time, we shall hear, our speaker will be Dr. Martin White from University of Port Elizabeth, which is South Africa, by the way. And Alyosha, Maria will send you some of his data, his address, etc., because he is a little bit uneasy because he thinks that he has no connections with us. Yes. So Maria will send you his data, and you will send him everything what it is possible about former talks, etc., about history, maybe of our seminar. And of course, what is the money? Maybe he will ask something else, some questions, but you will write him. Okay. So thanks for all for attention. We shall meet again after a week. So we leave. Okay.